In the previous video, I showed you a demonstration where air was blown through a horizontal tube where the width of the tube varied as you went along the horizontal direction. In that demo, the different segments of the horizontal tube were connected to vertical tubes, and those vertical tubes were connected at the bottom. In that demo, you saw that air would flow at different speeds through different segments of the horizontal tube. Because the air was flowing at different speeds through the different segments of the horizontal tube, you had different pressures in those different segments. Because you had different pressures in those different segments, that led to different liquid levels in those connected vertical tubes down here. In this video, we're going to do an example problem based on that demonstration. In this problem, we're going to solve for the pressure difference between the two horizontal segments, and we're also going to solve for the height difference between the water levels in the two vertical segments. We are given the density of water, 1,000 kilograms per cubic meter. The density of air, now the density of air depends on temperature, but let's say that at this particular temperature, the density is 1.29 kilograms per cubic meter. Let's say that the flow speed of the air in the narrower horizontal segment is 20 meters per second. The inner diameter of the narrower horizontal segment is 1 centimeter, and the inner diameter of the wider horizontal segment is 2 centimeters. So with that, let's start trying to find the pressure difference between the wider horizontal segment and the narrower horizontal segment. We're going to start with Bernoulli's equation over here, which I introduced you to in an earlier video. Bernoulli's equation says that this particular quantity here is a constant as you follow the flow, this quantity being pressure plus density times little g times vertical height plus 1/2 density times flow speed squared. That quantity is constant as you follow the flow. So to begin calculating for this problem, let's just take Bernoulli's equation and express it by saying that this quantity would be equal evaluated in segment 1 and evaluated in segment 2. So to start our calculation for this problem, let's take Bernoulli's equation, and in particular, let's take this version of Bernoulli's equation, which says that the quantity evaluated inside one of the horizontal tube equals that same quantity evaluated inside two of the horizontal tube. So I'm just going to copy this over. So I have P1 plus rho g y1 plus 1/2 rho v1 squared equals P2 plus rho g y2 plus 1/2 rho v2 squared. Notice that Bernoulli's equation here references the vertical coordinate in segment 1 and also the vertical coordinate in segment 2. Now, I haven't actually introduced a y-axis yet, but let me do that. And at any rate, when I introduce that y-axis, you can see that the vertical coordinates of those two segments are going to be the same. This is a horizontal tube here, and as such, y1 would be equal to y2, and we get cancellation here. I should also be careful here. We have two fluids in this problem, and the fluid which is flowing through this horizontal tube is air. So where I have rho for density in these equations, I should put in the A subscript for air. So it looks like we are almost there. The problem is asking us to solve for P2 minus P1. So let's just rearrange to get P2 minus P1. So I'm going to take this term here, 1/2 rho v2 squared, and put it on the left with a minus sign. Then take that P1, put it on the right with a minus sign, and I get 1/2 density air v1 squared minus 1/2 density air v2 squared equals P2 minus P1. Now notice how close we are to solving that first part of the problem. We have isolated P2 minus P1. And if you look at the left side of the equation here, the only thing which is not given is V2. We are given V1. How then are we going to get V2? Well, remember the continuity equation from earlier, which relates the flow speeds in the two different parts of the pipe. So if this part of the pipe has cross-sectional area A1 and this part of the pipe has cross-sectional area A2, we then have A1 V1 equals A2 V2. At this point, I would invite you to try to finish the calculation for P2 minus P1. We are given V1. You can then use the continuity equation to get V2. And once you have that, you have everything you need to substitute here and get the pressure difference P2 minus P1. And when you try that, check and see if you can get the right units for pressure to come out. And those would be newtons per square meter, or in other words, pascals. Give that a shot. All right, so I'm going to start by using the continuity equation to calculate V2 from V1. I'll start by writing the continuity equation. A1 V1 equals A2 V2. Solving for V2, V2 equals A1 V1 over A2. Now here I'm going to use the formula which expresses area in terms of diameter. So I've shown that to you in a couple of videos already. So area 1 would be pi over 4 times diameter 1 squared. Then we have flow speed 1. Area 2 would be pi over 4 diameter 2 squared. So cancel the pi over 4s against each other. And we have V2 is equal to, all right, let's plug in diameter 1, which would be 1 centimeter. That is squared. V1 is 20 meters per second. Then we have D2 squared. That would be 2 centimeters squared. So substituting and checking units, we get V2 equals 5 meters per second. Okay. Coming back to Bernoulli's equation here, I'll call that equation 1. We have P2 minus P1 equals, and I'm going to take this expression that's over here on the left and factor out density of air over 2. So now the right side would be density air over 2 times the quantity V1 squared minus V2 squared. So let's make our substitutions. Density of air is 1.29 kilograms per cubic meter. That's divided by 2. And then V1 is 20 meters per second. That is squared minus V2, which we just found to be 5 meters per second. Quantity squared. Now, if you punch this into your calculator, I believe as a numerical value, you will get 242. However, we'd like to make sure that we actually have units for pressure here. So we are looking for pascals, or in other words, newtons per square meter. So let's see if we can get newtons per square meter out of this. We have kilograms per cubic meter out here, and then inside the square brackets, meter squared over second squared. Now, what I'm going to do is cancel one factor of meter between the numerator and denominator. And when I do that, I get kilograms times meters over meters squared times second squared. But now look at this. Just exchange the order of second squared and meters squared, and I get kilograms meters per second squared times 1 over meters squared. So this is a Newton. And then we have newtons per square meter, which is the same as a pascal. So our pressure difference is 242 pascals, which would be the correct unit for pressure. Now let's move on to part B, which is to find the height difference between the liquid surfaces in the two vertical segments. Now, the idea here is that air has a low density compared to water. So if I start in the air up here and then move downward, going vertically through the air pressure up here and the air pressure down here would be about the same. Again, air pressure does not change very much when you move vertically through the air because of the low density of air. Similarly, if I go to the wide side now, the air pressure up here is P2. Now, if I start here and go down to the liquid surface below, the pressure down here would still be about P2. Now I'm going to use an idea which I argued in an earlier example problem involving a U-tube. The idea here is that if the pressure at the liquid surface on the right side is P2, then the pressure at the same depth on the other side would also be P2. So anyways, if we're just looking at the left side now, we have pressure P1 at the liquid surface, and then at a depth H beneath that surface, the pressure is P2. So to solve part B, I can use our equation from the previous module, which gives pressure as a function of depth in a static fluid. And if you recall that equation, what it says is that the pressure at a particular depth in a static fluid, which is here P2, equals the pressure at the surface, which is here P1, plus the density times little g times the depth beneath the surface. In this part of the problem, the fluid that we're dealing with is water, so I will put in a W subscript on the density. And now we can solve for that height difference between the water on the two sides. So just do the algebra to isolate the H. We get H equals P2 minus P1 divided by density of water times little g. And since we've already solved for this pressure difference, we can just make our substitutions now. So P2 minus P1, we already found that that was 242 pascals. Then density of water is given, it's 1,000 kilograms per cubic meter. G, as usual, 9.8 meters per second squared. Now let's do the unit checking here. Remember that a pascal is a Newton per square meter. Then in the denominator, I have kilograms per cubic meter and meter per second squared. Now, if you look at the denominator here, meters over meters cubed is 1 over meters squared. We also have 1 over meters squared in the numerator. So 1 over meters squared up here cancels 1 over meters squared down here. Let's take that 1 over second squared in the denominator and make it just second squared in the numerator. So I have newtons times second squared over kilograms. Now a newton is a kilograms meter per second squared. But then I also have here second squared over kilograms. So second squared cancels second squared, kilograms cancels kilograms, and we are left with just meters as we would expect for a height. So our height would be however many meters. When you punch everything into your calculator, I hope you will get 0.025 meters. So now we have solved an example problem using Bernoulli's equation, but notice that we also used the continuity equation, and we also used our old formula for pressure as a function of depth that we learned about in the previous module. In the next video, we will have a second example problem using Bernoulli's equation.